Okay, so welcome to video 2.4. We are going to learn now how to calculate the time that it takes for an object to cover a certain displacement while it's accelerating. We had previously learned that you could, if the object was traveling at a constant velocity, you could calculate the time using this equation by just taking how far it had to go and dividing it by how fast it was going, and that would give you the time. But the problem is that if the velocity is changing, that becomes a little bit more difficult. So one way to do it would be to use what I showed you guys before, which would be find your average velocity and plug that into this equation down here. You can find the time that way, and that absolutely works. But a lot of times that's not practical because you won't know this final velocity. All right, so I'm going to show you a super secret ninja shortcut to do this. All right, so here we go. Kaboom. All right. So this example 4, again, is kind of a continuation from the previous example. So example 3 is on the last video. It says, let's work the other way. What I mean by that is, in the last video, we were using this equation to find displacement. So now we're going to work the other way, and we're going to be given the displacement, and we're going to try to solve for the time. Okay? So that is where we're headed here. All right? So it says, suppose Roy was going to roll a ball down a ramp. If the ball began at rest and accelerates at 6 meters a second squared down the ramp, then find the time it would take the ball to roll each of the following distances down the ramp. All right. So to solve this, we're going to algebraically rearrange an equation. I'll come back to that in a second. Before we do, let's take a look at this at part A. Let's write down what we know for part A. So here are the things we know. First of all, the problem tells us the ball begins at rest. So our initial velocity is going to be 0. Because the ball was not moving when we first let go of it. We know the acceleration is going to be 6 meters per second squared. And we're trying to find the time that it's going to take for it to cover this displacement. So our displacement is going to be 30 meters. All right. A quick note about signs. You could, if you wanted to, argue that both the acceleration and displacement are negative because it's rolling down a ramp. I am, for simplicity, going to picture down the ramp as being forwards. The idea is that the ball's always rolling the same direction, forward down the ramp, so let's just make that direction positive, and then we don't need to worry about our negatives in this problem. All right, so we need to find our time. So again, like I was just saying, we can't use this equation because we don't know the average velocity. And finding the average velocity would require us to know the final velocity, which there's not an easy way to find. All right, so the fact that we're given the displacement clues us in that we need to use maybe a displacement equation, and because we know the acceleration, maybe using this makes some sense. Okay? So it turns out you can do some algebra, which I will not bore you with here because this is physics, not algebra, but you can do some algebra and rearrange that equation to get this. Ooh, look at that. All right? And it says that to calculate the time, you take 2 times your displacement, divide it by your acceleration, and take the square root of the whole thing. You can only do that. This is super important. You can only do that if your initial velocity is 0. Okay? If the initial velocity is not 0, it is significantly harder to find the time. You actually have to use the quadratic formula from algebra class. We will not be doing that. That's the sort of thing that you might see in your honors physics class, but we're not going to be doing that. Okay? So now that we've got this equation, if you take a look over here at what we know here, this is, whoa, that was not what I wanted to do. If you take a look at what we know over here, this equation is now pretty easy to solve. Because look, we're trying to find the time. So it's 2 times our displacement divided by our acceleration, square root it. Our VI is in fact 0. So you just plug in your numbers. You get 2 times our displacement is 30 meters. Our acceleration is 6 meters per second squared. Don't forget to take the square root. So 2 times 30 is 60. Divided by 6, you end up getting the square root of 10. You end up getting seconds squared because the meters cancel out here and here. So you get the square root of 10, which is, I apologize, I need to grab a calculator here. Let me do this real quick. Square root of 10 gives you 3.16 seconds. Okay? So that's the deal there. It took us 3.16 seconds to fall, or to roll 30 meters down the ramp. Okay? So, pause it at this point and write it down. I'm going to erase all this. And let's do this. So over here, we just figured out that the time was 3.16 seconds. Okay? So, now, if you repeat the process here for part B, you know kind of the same stuff. You know your initial velocity is 0. You know your displacement now is 60 meters instead of 30 meters. You're still looking for the time. You still know your acceleration is 6 meters per second squared. So it's the same process. T equals 2 times the displacement over A square root. So you get 2 times 60 meters divided by 10 meters per second squared. No, sorry. Six meters per second squared, because it's rolling down the ramp, it's not in free fall, and take the square root. So this time you get the square root of 20, which gives you, all right, there's a reason I'm going through all of this, so bear with me here for a second. And so you get 4.47 seconds. All right, so there's our answer for that. Again, pause it, write it down if you haven't already done so. And so here, the time is 4.47 seconds. All right. All right, I will not bore you with this last calculation, but if you do the last one, you end up getting 6.32 seconds. All right, so here's the whole point of this. Check it out. Well, first of all, we were able to find the time of an accelerating object given the displacement, which is sort of the whole point of this video. The other thing I want to point out is this. Look, in part A, the displacement was 30 meters, right? In part B, the displacement is 60 meters. It's going twice as far. All right, and students have a common misconception, and they think, oh, well, it's going twice as far here, so it should take twice as long. But if you look at our results here, that is twice as big, right? The displacement's twice as big, but the time is not twice as big, right? In other words, double the displacement doesn't give you double the time, all right? And the reason for that is because it's accelerating. If you picture this 60 meters as being 30 meters and then 30 meters, what's happening is the ball is speeding up. So the first 30 meters takes 3.16 seconds. The next 30 meters takes less time because the ball's already moving. It's moving faster. And so the second 30 meters takes less time than the first 30 meters. So you're not just doubling the time. Okay? And that is what, down here at the bottom of the screen, whoa, it says, let me move all this garbage out of the way. There you go. All right? So, if you are given the displacement and asked to find the time of an accelerating object, that is how you do it. All right. Once again, here is a list of all the equations that you should have at this point in the chapter. Please make sure you have them written down if you didn't write them down in the last video. I'm going to stop there because I told you 5